Schoology every single grade, and that's the story of the evolution of Wade.
BC 5-5, you better know your graphs. Just the basics, not the crazy graphs, just the basics, right? But you gotta be rock solid in graphing from now until probably through the next 12 sections, all right? So, first of all, we start with an easy one. Y equals x cubed, y equals 4x. Boom, right? Y equals x to the third, snake. Draw a picture. Snake from integrated 3 goes to the origin. Now, y equals 4x. Isn't that mx plus b, right? Isn't that just a line? When you plug in 0, isn't 4 times 0 also 0? So it passes through the origin 0, 0, of course. But it's a very steep slope of 4. Rise 4, run 1. Just draw me a steep line. Now, play the game. Don't make the line like this, because then it won't enclose a space. All right? Play the game. Make it a little steeper, pretty steep here, kind of like that. Okay, because the line and the snake will eventually intersect each other. As a matter of fact, at the origin, they'll intersect each other somewhere up here, and they'll intersect each other down here. So you have to kind of use some drawing strategy here because it should enclose a space. What's one of the major themes in this chapter? Find the area of the enclosed region. So it has to be enclosed, right? Okay, so because the snake x cubed is stronger than the line x to the first, the snake will eventually catch up to it and surpass the line, of course. The snake will go like this, the line will go out like that. Snake is way steeper, way higher. So you should have a little enclosed space. But how do we find shaded area inside of some kind of space in calculus, right? Because these don't have simple formulas like pi r squared, base times height. So remember, you need to know the boundaries, right? Don't we integrate from left to right as Darboux discovered? Remember this? So we kind of need to know what these intersection points are. We know that one's 0, 0 by trial and error, but we do need to get these two. Okay, remember, intersection points are when you set two curves equal to each other. So this is going to be mandatory right here. Now, a novice math student would divide both sides by x and somehow think that's going to give them all the proper solutions. Oh, be careful. What did Mr. Wade say so many times? If there are multiple 2 or more powers of x or types of x, the only way out is to get it equal to 0. Remember those wise words, even back in integrated 3? X cubed, x to the first. 2 different powers of x. You don't divide both sides by x. You must subtract the 4x and get it equal to 0 to truly get all the solutions, okay? And the highest power should be kept positive. That's why I subtracted the 4x, not the x cubed. Now, step 1, get it equal to 0. And unless you had like all x cubes, okay, then you wouldn't have to, right? But we had 2 different types of powers. Step 1 equal to 0. Step 2, factor out the GCF. I hope before I even say step 2, you're already thinking it because I've said it so many times this year. Factor out the GCF. Step 3, set each group equal to 0, just like integrated 3. X equals 0 is the first one, and x equals plus or minus 2 are the solutions of the second one. Oh, guess what? This is negative 2, that's positive 2, and of course, the origin is 0. All right, we've got 3 intersection points. Now you can integrate. But there's a new twist today. Our old buddy, Jean-Gaston Darboux, discovered that the area of any space is the integration from left to right, that is left x to right x specifically, of the vertical distance, top y minus bottom y. This is in very colloquial terms here, all right? Very unofficial terms, but guess what? It works. Of course, it's way more formal in textbooks, but I love writing, basically interpreting calculus into very simple English for my students. That's why they get such great scores and why they learn so much from me, because I like to break it down into simple terms. Okay, don't overcomplicate stuff just because you're smart. All right, so left x to right x, top y minus bottom y. We also call this vertical distance. When you write an integral, you write a dx. So this is basically area of any space in the world that we need to find 2-dimensionally, right? Okay, we haven't even gotten to 3-dimensional stuff, right? So here's the scoop, kids. when you integrate the vertical distance top y minus bottom y, and when integration is able to stack an infinite number of vertical distances in there to make it work, because remember, integration is an infinite sum, right? Do you see, if you draw just like a little sample vertical distance here, do you see how the snake is on the top and the line's on the bottom? Now go over here to this region. When you draw a vertical distance, the line's on the top and the snake's on the bottom. That's a different equation, right? This vertical distance would be x cubed minus 4x. This vertical distance is 4x minus x cubed, top minus bottom, right? Two different formulas. They're almost the same, but they're flipped. Okay, you can't integrate two different formulas with just one integral. So if you look up here, if you notice the two different spaces, you need two different integrals. So I've got a new thing for you to remember. If the upstairs or the downstairs ever change, you have to rewrite another integral to handle that change. Okay? In this case, the top and the bottom both changed. They switched, but they both changed to something different. Okay? So therefore, you must have another integral when the roof or the floor ever change. Either one of them, even if one of those change. So the only way to do this thing right here, just in general, would be to integrate from -2 to 0 of top y minus bottom y, which is snake minus line. And that integration, as Darboux discovered in the 1800s, would basically find the area of that little shape right there, plus the rest of the area from 0 to 2 of top y minus bottom y vertical distance, 4x minus x cubed. As we said, they switch. And that would give you the area of the other little group right there, okay? And this could be something that they're manufacturing. This could be a propeller for a plane or something, who knows? So that gives you the total area, all right? Now, in another twist, you could just integrate all this right here. I do have a shortcut for you. In the rare case that these two pieces are symmetric and they are the same size, it's actually called rotational symmetry. It's not y-axis or folded symmetry. But if you rotate this around, they do match, okay? They are the same size. So only when they're the same size could you do just one integral and then double the result and get the same thing, okay? Doesn't always work though because it's usually asymmetric. So here, yes, you could just take, this is probably the easier integral because it doesn't have a -2 in it, right? Let's take the positive one. Let's keep it positive. Double the area from 0 to 2, and you'll get the same answer. And now the rest is just review. Keep the 2, keep the parentheses. Integration of 4x would be add 1 to the power, divide by the new power, that'll reduce, minus x to the add 1 to the power, divide by the new power, evaluated from 0 to 2. And now, of course, we do our plug in the top, plug in the bottom. So 2 stays. Let's reduce this. Let's make that 2x squared. So you would get 2 times 2 squared is 2 times 4, which is 8, minus 2 to the 4th is 16. Know your powers of 2, right, from integrated 3. 16 over 4 is 4, okay? Minus, the 2 carries again, but then if you plug in 0, it's a polynomial, so you actually do get 0, but not always, remember. All right, now, 8 minus 4 is 4, and you just have to do 2 times 4. By the way, each region, this is kind of amazing that it's not a fraction or an irrational number, because a lot of areas are irrational, by the way. Each region is exactly 4 square units. How about that? Huh. You could actually take this, if it was made out of Play-Doh, and remold it into a 2 by 2 square that's exactly 4. How about that? Very cool, right? Okay, so there were 2 4s, and this is what it's telling you. There were 2 4s, and then that makes 8 total. And there's your area. There you go. So now you're starting to get where you can integrate anything and find the area of any shape, right? Which is amazing, incredible. So now we have this one. This is a cool problem too. Y equals the natural log of x minus 2. Okay, you better know your graphs, right? All right, so first of all, if you think this is back in integrated 3 where plug in something for x that makes the inside 0. X equals 2. Plug that in, you get natural log of 0. The natural log of 0 is undefined. You can only take the natural log of a positive number, not 0 or a negative number. So the first thing you do is you make the inside 0. This works for natural logs, it works for square root, cube root, x squared, x to the third. It works for all that stuff we did back in integrated. Oh, even exponentials, exponential growth and decay, it still works. So I like to make the inside 0. Why is x equals 2 undefined? Because at 2, there is a vertical asymptote. Right there. That's a little curvy, but pretend like that's a straight vertical asymptote. Now, the other thing I used to say all the time in integrated 3 was plug in a number for x that makes the inside 1. 0 and 1 are the easiest things to deal with in math. So plug in a 3, and that would give you y equals natural log of 3 minus 2. That's natural log of 1. Natural log of 1 is 0. Your graph must hit the point 3, 0, and that's very important for the integration, by the way. So I'll put a point at 3, 0. Now, vertical asymptote, x-intercept, then you have to know your curves. If you don't know what natural log looks like, then you'd be stuck. You'd have a line and a dot, big deal. Oh yeah, Mr. Wade, natural log tries to get to the force field, but it can't quite touch the force field, and then it comes up through the 3 very steep, and then it really levels and becomes shallow. That's how you graph natural log. You can do that way quicker than I explained it though, okay? So asymptote, the x-intercept, the curve, you're done really quickly. And basically it's a natural log graph shifted right to, of course, is what it is. Okay, now, x equals 5. That is x equals number. X equals number is always a vertical line through that number. So everybody picture 5 on the x-axis, and then forever x equals 5. X coordinate permanently 5. That could only be a vertical line. Again, my vertical line looks terrible, so just go with it. All right, and then the x-axis is the third of the 3 boundaries. X-axis, oh, you see right here, there is one shape that touches the natural log curve, the vertical line x equals 5, and the x-axis simultaneously. Shading optional, but fun. This is how you see it written on the AP test, by the way. It's a capital R, it's in italics. If you notice, it's like barely slanted off to the side, and then it's in bold. So that's kind of an AP thing I'm getting you used to for the testing purposes. So, graph region R, got it. Find the vertical distance. All right, let's pick just any old point on the natural log graph, go straight down to the x-axis. The vertical distance is, of course, simply top y minus bottom y. Easy, right? The top y, the upper y, is natural log of x minus 2. Those are the upper y coordinates. Says right there, y equals natural log of x minus 2. So that's the top y. Minus the bottom y. The bottom y is the x-axis, which would be 0. That's basically y equals 0 in disguise, x-axis. So your vertical distance, just drop the 0, is simply natural log of x minus 2. Sometimes it is just the equation and not multiple equations. Okay? Got it. So now let's go up here and draw a horizontal distance. I'll use a different marker so you can see a little bit better. There's a horizontal distance. Of course, that's going to be used for a lot of real life things and calculus things. And so, all right, what's the equation for a horizontal distance? We did it the other day. Wasn't that right x minus left x? The way that you can look at something in your brain and calculate how far across it is, right? So now the right x, okay, the right x coordinate is permanently 5, isn't it? You see this point right here? The right x must be 5. Minus the left x. Okay, the left x is whatever the x coordinates are on this natural log curve right here. Okay, isn't that the equation y equals natural log of x minus 2? That's the equation that governs where the points lie. But wait a minute, left x? That doesn't have x by itself, does it? I've got to get x alone. I've got to solve for x here, right? It tells me what the y coordinates are, but not the x coordinates. So maybe we should do a little aside over here someplace. go off and find some space here. If the curve is y equals natural log of x minus 5, I've got to get x by itself to tell me all the x coordinates, the formula for the x coordinates, don't I? Well, we got to get rid of this natural log because the x that we're trying to save from the house fire is like locked in the house, and then somebody put a natural log lock, I guess it's a natural lock, on the front door, and I got to get the lock off. Well, where's the key? All right, well, we're firefighters. We're going to knock it off with an axe, all right? And what is our axe? The letter E. That's what gets rid of natural log. And if you do it to the right, you do it to the left. Now you just broke off the lock and you just got in the house. The house is on fire. The house is on fire. Where's X? I'm over here, right? Okay, so e to the y equals x minus 2. Aha! There's X that we're trying to save from the house fire, but there's this minus 2 in the way. It's like somebody put a mattress over top of them, all right? Get that mattress out of here. Add 2 to both sides. That gets rid of the mattress, right? And X is finally by itself. It's e to the y plus 2. Now you just saved X from the house fire right there, okay? That's just some random analogy, but you get it, hopefully. Okay, so all the X coordinates on the natural log curve shall be e to the y coordinate plus 2. How about that? So the left X is, make sure you put a parentheses. It's the quantity e to the y plus 2, okay? Go ahead and distribute that minus. So 5 minus e to the y minus 2 equals 5 minus 2 becomes 3 minus e to the y. So that is the official formula of the horizontal distance or the thickness across this shape right here, how wide it is. And you can just imagine, just let your imagination run wild. You're all very clever, creative art students. Just imagine all the real life applications of trying to figure out like how wide something is across for architectural purposes, for engineering purposes. I mean, they're just infinite possibilities, okay? And yes, they use this all over the place in real life. Now we've got a formula. Now let's get down to business. 2 integrals that find the area of the shaded region because that's super important. Area equals, well, we've been talking about it, haven't we? The integration from left to right, which would be, where does this exist? 3 to 5? Well, it's a good thing you know how to graph, because didn't the 3 come from the natural log graph, and then the 5 was given, but we had to know those boundaries, didn't we? Then don't you just simply integrate the vertical distance, or the integral stacks up, sums the infinite vertical distances, right? So that would be what? Vertical distance. We already did it. Actually, we don't even need a parentheses. Natural log is basically its own parentheses. Integrate the vertical distance, top y minus bottom y, from 3 to 5, and put a dx on it. That's it, okay? That's going to give you the exact area under the curve. Of all the things we've integrated this year, we don't know the integration of natural log. You're probably scratching your head saying, Mr. Wade, how is that possible? We know how to integrate everything. We have never integrated natural log. We've only taken its derivative. Look at the board of 9 things that I need to know how to most commonly integrate off the top of my head, or however I said that before. You see it up there? Nope, there's no natural log over there. Integrating natural log is not done in a super common fashion, so you know what? I think we might need a backup plan if we don't know how to integrate natural log. And sometimes your integral might be something that can't even be integrated. That can also happen, okay? Natural log can be integrated, but if you get a function that is not even integrable, then you have no prayer of finding the area and you need a plan B. Here's the backup plan. I give you the alternate area formula. Instead of stacking vertical distances across, couldn't you stack horizontal distances from bottom to top? Now, wouldn't that be clever? Mathematically, it would be the same thing. How do I sum up infinite horizontal distances? The integral sums up infinite things, right? From bottom to top. So here's your new formula. Bottom y to top y coordinate. What's the range instead of the domain? What's the frame this way? And then what do you actually integrate this time? You stack the horizontal distances. So you could put horizontal distance, or I guess you could put our official formula, right x minus left x. Either way, whichever way you want to write it. With a d, oh, I'm going to talk about this too because this is a new twist. With a dy. Now we've seen a lot of dx, we've seen a little bit of du, we've even seen dv. I don't think we've seen dy yet. When you stack things this way, like in a y-axis kind of way, you're stacking upwards, you have to use a dy because these are y numbers and that's dy. These are x-axis numbers, that's dx. So for the first time ever, we're going to have to involve dy. New twist, all right? It's the same thing, by the way, same method. So here's my alternate attempt. Bottom to top. What is the bottom y of this shape? Well, it's on the x-axis, it's 0. The bottom y is 0. What is the top y? Now, that's something we don't know yet. We don't know how high the shape goes. Well, normally, when you find an intersection point, don't you set two things equal to each other, both equations? We did that earlier, didn't we? On the snake graph over there. So you set two things equal to each other like, what's this, natural log? So that's the natural log. What's this? Isn't that x equals 5? Well, this is the one time you don't set two equations equal to each other to find intersection. The only time, when you have a vertical line. When you have a vertical line, that's x equals 5. Couldn't you just take 5 and put it in for x in the other equation? Basically, if you plug in 5 to the natural log, won't that just take you up the elevator until you stop on the natural log? Okay, so you're seeing the only time that intersection does not require setting two things equal to each other. Take 5, put it in there, and that would be the coordinate 5, comma, what is that, natural log of 3? 5 minus 2, right? There you go. The 5 is the x, but we're looking for the y right now. It's natural log of 3. So we're going to stack our horizontal distances, or integrate from 0 to natural log of 3, stacking this way. And then horizontal distance, right x minus left x, we already did it. 3 minus e to the y, in parentheses. 3 minus e to the y. Notice that the function contains y's, not x's. That's another reason you have to have dy. And those are y numbers. So everything's in terms of y now, all right? Now today we're just setting up the integrals. We're not going to actually integrate them. Let me go ahead and put a box around this. That was my setup, my first attempt. Here is my alternate attempt. And there will be one problem, of course, at the end of the chapter where you are required to find the area, and this one's a trap and you get stuck and you've got to try plan B. It's good to have alternates in calculus, all right? So now, just to go through this to make sure you understand, all right, know before you go. Even though this is just a setup, I want all of you to know how to integrate this so you can do it later. So we won't solve the whole problem. Let me just show you how to integrate it. Does everybody remember that the derivative of 3x is 3? Does everybody remember that the integration of 3 goes back to 3x, right? Except it's in y world. So the integration of 3 is 3y. It is just like 3x though. So 3y minus. Does everybody remember that the derivative of e to the x is e to the x? That the one thing that stays the same, right? So isn't the integration of e to the x also e to the x? Isn't the integration of e to the y e to the y? Okay? And if anybody's wondering, wait, shouldn't it be implicit? Remember all the implicit derivatives where like the derivative of x is 1, but the derivative of y is y prime. Why are we not talking about implicit? If you're thinking that, don't worry, it does not affect this at all. dy means that the y is acting like an x. dy means the y's are normal, okay? Any other variable would not be normal, but it just means y's treat them like x's, okay? That's why. So that's why. Evaluated from 0 to natural log 3, and then you do your whole top minus bottom thing. But do you see how easy it is to integrate 3 to 3y? And e to the y stays the same, right? That's so easy to integrate. Okay, we've never even talked about the integration of natural log, so that's why over here you're really stuck. Now I'll give you a little secret if you want it. You could integrate this by integration by parts, okay? This is actually 1 times natural log of x minus 2. You ready for this? Okay, if you had to do it, which you might have to eventually in this class, late method, the late acronym. 1 is algebraic. It's x to the 0. X to anything is algebraic, right? 1 or x to the 0, algebraic. Natural log is, of course, logarithmic. The higher one is u, and the 1 is your dv. So actually the 1 gets the dx. So your dv is dx, and your u is natural log of x minus 2. You go back to chapter 4, you do uv minus the integral of v du, and you can do it, all right? So if you ever have to in the future. That's just totally for fun. Otherwise, skip to the next problem. All right, let's try 2 more sets of this just to make sure you feel good about this. So we need to graph the region R enclosed by arcsine of x equals 1, and the x-axis. All right, so, oh, Mr. Wade, I forgot how to graph arcsine. Okay, you don't graph it every day. Quick reminder. Doesn't sine go through the origin? Okay, doesn't sine have a peak at pi over 2 comma 1, right? And then doesn't sine come back to the x-axis at pi comma 0. Know your graphs, know your sine graph. Now, how do I quickly make an arc sine graph if I forget? The arc sine is the inverse of sine. All the points are switched backwards, okay? So the arc sine, if you can kind of just have a mental image of those 3 points, I mean, that's really all it takes. The arc sine is the origin reversed, which is the origin, 1 comma pi over 2, and 0 comma pi. And you can very quickly graph this, okay? So let's see, we'll put it down here. All right, origin, right 1, up pi over 2. Okay? Right or left 0, up pi. And then as soon as you see that, hopefully you have kind of a recollection that, wait a minute, the sine graph that used to have peaks at the half pies, all the peaks become right edges at the half pies, okay? Or all the valleys become left edges. And then you have like this, and it's just a sideways sine, kind of twisted, all right? So that's the easy way to graph arc sine, the quickest way probably, is just to kind of think of the points reversed, if you ever forget. And then you have to remember that other thing I talked about before. The inverse sine is this thing going forever, but it fails the vertical line test. It keeps doubling over itself. Does not pass that vertical line test, it's not a function. But arc sine is a function. Oh, arc sine is just from left edge through the origin to the right edge. So just that little piece of it is arc sine. And just since I'm on a whiteboard here, or a fake whiteboard, I'll erase the rest of it. You don't have to, but that little piece, it's kind of like a snake, kind of like x cubed. That little piece is arc sine, okay? All right, arc sine, x equals 1. That's a vertical line. So x equals 1, that is 1 actually. And the x-axis, aha. There's only one shape that touches the x-axis, the vertical line x equals 1, and arc sine all at the same time. It's that little curvy looking sort of a triangle in there, all right? Remember the left x to right x? 0 to 1. 0 to 1, left to right. Integration of the vertical distance. Top y minus bottom y. Let's check out a little vertical distance right here. Okay, very easy. The top y is arc sine of x. That's what makes those y coordinates happen. Arc sine of x, oops, minus the bottom y is on the x-axis, which is 0, with a dx, because the dx must match not the letter here, the dx must match the 0 to 1, which is on the x-axis direction, okay? Then, subsequently, this will have to also be an x, yes. The problem is that students accidentally put like y functions here sometimes, and then they put dy, but then they're not looking at the numbers. They're looking at their miswritten variable over here. Okay, so always match the d to the direction that these are going in an x direction as opposed to a y direction. And then make sure this has an x to match that. That's probably the best way to do it. Okay, integrating arcsine, fat chance. Is that on our board of 9 things that we most commonly integrate off the top of our head, which is kind of cut off now? You can't quite see the secant squared up there. No, that's not on our board over here, is it? Okay, again, I'm sloping downward. But you will not be able to integrate arcsine in this class. Okay, forget it. That's a way higher level of calculus. So now we're going to do hot shot. What are you going to do on the test when you get this? If you say, I don't have to learn that alternate method, Mr. Wade. Oh yeah, you need it. Okay, what's the alternate method? Let's find the area by stacking horizontal distances. Infinitely many, infinitely skinny, right? Or infinitesimally small. So I'm going to stack from bottom to top, low y to high y, 0 to pi over 2, the horizontal distance, which is now going to be right x minus left x. So clever how this all works, right? Hopefully it's all like gelling in your brain right now, like, wow, it all came together, Mr. Wade, this works. Okay, the right x is 1, because it's that vertical line, right? Minus the left x. The left x would be a coordinate on the arcsine graph. So I guess I'll just put, see, here's the mistake right here. Students will just take arcsine of x and just throw it down here. Hold on a second. Let me put a little parentheses here. 0 to pi over 2. Isn't 0 to pi over 2 a y direction? So that must go with dy. That's mandatory. So if you take arcsine and drop it right in here, you can't have dy and x's. dy says you have to have y's in here, and hopefully that'll trigger your brain if you're about to make a mistake, okay? The left x on that curve, that's solved for y. That's not solved for x. Get x by itself. How do you get rid of arcsine? You do the opposite. Normal sine. Take the sine of both sides, okay? Let's do that off to the side somewhere. Sine of y equals the sine of arcsine of x. But what does sine do? Sine breaks off arcsine. They work against each other. It's the only thing that can break it, okay? And you end up getting x is equivalent to the sine of y. That's what x is equivalent to. All the x coordinates on the arcsine graph, all the x coordinates are the sine of y. Okay, guess what? You're not going to be able to integrate arcsine in this class. You all know how to integrate sine, right? Matter of fact, it's a negative sign, okay? Know before you go. It's just a setup problem, so all you had to do is set it up, but for later purposes, you do have to know how to integrate this. What's the integration of 1? 99% of the time, it's x. This time with the dy, it's technically y. What is the derivative of negative sine? Negative cosine. So what's the integration of negative sine? Positive cosine. All right? And by the way, I haven't mentioned this today. Yes, when you integrate, you always divide by the chain rule. It's mandatory. The bases so far have just been either x or y. So the chain rules are all 1, so that's why we're not mentioning it, okay? So you would do y plus cosine y, then you would plug in top minus bottom, and then you could go from there, all right? That's all you have to know there. Okay, last section. The last group is over here, and if there was ever a section I've taught you all year long where thou shalt know thy graphs, this is the one, let me tell you. This is the one, because notice we're getting all kinds of just random graphs today, and you've got to know what they look like. So 2x plus 4y equals 4. You've got to look at that in a millisecond and know what it is. It's x to the first, it's y to the first. It's a line. Nothing more than just a simple line, okay? Now, graph the region. Okay, we mentioned this before. This came up in another lesson, actually. How do you graph a line super fast? Well, you get the x-intercept, you get the y-intercept, and you connect the dots, okay? How many points do you need to draw a straight line? 2. What are the easiest 2 points to get in the world? The x-intercept and the y-intercept. So the first thing I would do if I were you, if you wanted to make it easy, plug in x equals 0 to get the y-intercept. 0 hides this. 4y equals 4. Y equals 1. Okay? I'm teaching you how to be efficient. The most efficient graphers and problem solvers on the planet come from Mr. Wade's class, all right? And also Korea and China. So let's also plug in y equals 0. If you plug in y equals 0, we can go find x. So you take 0, you put it in for y, that hides that. 2x equals 4. X equals 2. Okay, quickly, right? You want to be an efficient grapher. You don't want to waste a lot of time graphing. So 0, 1. So it hits the y-axis at 1. And then x is 2, y is 0, hits the x-axis at 2. I'm going to make it look like it's a little bit more than 1. There's only one line in the world that hits those 2 points, right? See how easy this is? It's just y equals mx plus b in disguise with y is not by itself, basically, but we'll have to get it by itself. Axes, plural of axis. The line and the 2 axes all come together to enclose, not a kind of triangle, a triangle. Before we had like curvy triangles, right? No, this is exactly a right triangle, actually, this time. Okay, now, find the vertical distance. All right, let's pick a point on the line. Let's go straight down to the x-axis, and vertical distance is top y minus bottom y. Eventually, you will not have to write this formula anymore. Maybe now, because you're so used to it, you can just think it, okay? Think it, don't write it. Top y, what's the top y coordinate? The line's not solved for y. We need to solve that line for y, don't we? Get y by itself. All right, let me go over here, use some space. Let's subtract the 2x away. So 4y equals 4 minus 2x. Okay, we did this in an earlier, at the beginning of the chapter, the warm-up, we did this. Okay, like 5-1. Divide both sides by 4. 4 minus 2x over 4. Don't divide each one by 4 like maybe integrated 3 we would. Leave it as one consolidated fraction. That will make your life easier in a few minutes here. Okay, so top y coordinate on the line is apparently 4 minus 2 times x coordinate all over 4. So 4 minus 2x over 4 minus the bottom y, which is the x-axis, which is 0. There is the vertical thickness of any point on this triangle. Okay? All right, now for the final and one of the greatest problems we'll talk about, because this has major future implications. Find the volume of a 3-dimensional solid that is created by taking this triangle and rotating it around the x-axis. Does anybody know what happens when you take a right triangle and you rotate it around an axis and it goes all the way around back to itself again? If you're thinking a perfect cone, you're absolutely correct. Picture this point here, orbiting off the board, around the x-axis, back through the board to itself. Kind of look like this. We'll have to draw it sideways, of course, perspective, right? And then imagine this bar rotating off the board, and it would look kind of like this. Here's its mirror image, and that would make a perfect cone. Like those, you know those Halloween decorations that like unfold and they come all the way around to themselves? Or like Thanksgiving turkey decorations that you can get at Party City and you kind of unravel them and they come all the way around to themselves? It's kind of like that. Hey, here we go. It appeared out of nowhere. It's like one of these things that like opens up, you know what I'm talking about? And it comes all the way around to itself. Can I do this with one hand? Yes, I can. Like one of these. That's what's happening here, all right? This is flat on the board, right? But it's coming off the board and going around to itself, all right? Like that, okay? Here's the side view, okay? So to end off today with a groundbreaking thought that I want you to have in your mind for the rest of calculus, basically, to the end of the year, and as long as you're taking math classes. A cone is a stack of circles, infinite circles, because circles have no thickness, all right? Circles have a radius. Circles are two-dimensional. They have a height and a width, which is actually just the same. It's both the diameter, right? But they have no thickness. They're infinitesimally skinny. When you stack circles, you can make a cone. And we're going to start stacking circles in this class, okay? What did we do before? What is the main theme today? Area is a stack of vertical distances, or sometimes a stack of horizontal distances. And three-dimensional objects can be a stack of circles. So here's what we're going to do. The area of each one of those circles is pi r squared. But now let's talk about the radius. The radius of each one of these circles is a vertical distance. The radius is equivalent to that vertical distance at any point. And the radii vary, don't they? Because the radius here is the biggest in the shape, and then they vary. They get smaller and smaller and smaller. So when things vary in math, you need a variable, because the root word of variable is vary. Okay? It covers all the different possibilities right there. Now by substitution, watch this. Take this, substitute it back in here. The area of each circle in this picture up here, from the biggest to the smallest, which is basically 0, the area of each one is expressed by pi r, or vertical distance, quantity squared. This is genius, okay? Hopefully this is unraveling in your mind, just like that Halloween decoration. Hopefully you're thinking, oh my goodness gracious, this makes sense, Mr. Wade. This is like one of the foundations of calculus. Yes, it is. Okay, how do you square 4? You get 16, right? How do you square a binomial? You either FOIL it by itself or you don't even bother, because why would you FOIL right now? You wouldn't. You would leave it quantity squared. And don't anybody ever distribute a power across a subtraction sign. Don't you dare square each one of those, okay? Now, that's the area of what? Any circle, any singular circle by itself follows that pattern. You give me the x-coordinate, okay? Give me a random x-coordinate, like 1.6, plug it into this, it'll tell you the exact size of the circle coming off the board. But I don't want the area of just one circle. I want the three-dimensional volume for the first time this year. The three-dimensional volume of all those circles stacked up to make a cone, a conical shape. The volume. How can I possibly find the volume? I can find one circle. How can I possibly add up infinite circles? Nobody can add up an infinite number of things. Oh, yes, they can. Once integration was discovered. An integral is a stack of infinite things, or a sum of infinite things, from 0 to 2. You can actually do this three-dimensionally as well. I hope I'm blowing your mind right now. And then, what do you integrate? What are you stacking? Circle areas. There's the circle area. That's the integrand with a dx at the end. And then finally, just for one last step, why don't we take the pi over 16 as a coefficient and let's scoot it outside. So pi 16ths, integral from 0 to 2, and then what's left over? 4 minus 2x quantity squared dx. See, I moved the pi over 16 out to the front. That is the setup of the infinite circles stacked together that will give you real life volume. Wow, major lesson today, okay? Major breakthroughs in your understanding and your learning of calculus, okay? And then just for fun, if you want to know before you go, we won't integrate this whole thing, we will later, not yet, but know before you go, know how to integrate that when you do face it, okay? Just one step. If you'd like to add this to your notes, it's optional. You overachievers, you can do it. You leave the coefficient in front. How do you integrate 4 minus 2x to the second power? You don't do u substitution. I mean, you could. You don't need u substitution. The chain rule of the base is a constant, which means you can bypass u substitution. Don't you just do 4 minus 2x quantity to the third, add 1 to the power, divide by the new power 3, and if you don't do u substitution, divide by the chain rule, which is -2. Evaluated from 0 to 2. And then you just start plugging through all the algebra and trudging through all that stuff, and you get to the end, okay? So just to show you how you would do that, how you could do that, there you go. All right, that is actually AB calculus. We just got to it first, okay? But that's really cool stuff indeed, okay? Not even BC. All right, now we go on to 5-6 and a sample test, and we wrap up chapter 5.
Hold it now.
Find the region of the enclosed space, right? Or sorry, I completely blew that. Areas are irrational, by the way. This is exactly 4 for each one. Dang. Okay, it's basically a natural log scooted left to, sorry. You moron!